Hello and welcome to the video. And in this video, we will deal with the noise in MOSFET. And when we have a NMOS or a PMOS, so there is a current related to the gate voltage, and the current is from drain to source, and we have VGS and VDS. So the drain current is given as a function of ID, which is a function of VGS, and VDS. But as we are talking about noise, there is also a current source which is due to noise. So just like a resistor, we had current predicted by Ohm's law, and there was a some noise in addition. So here also the current is predicted by a square law model, and there is a small current source due to noise. So as a similar to resistor, we will describe the spectral density of the noise, and we can calculate the r.m.s value of noise in different circuits. So this is how we can represent the current source due to the noise in a MOSFET. And so we assume a noiseless MOSFET and some noise source in parallel. So as we know, MOSFETs operates in deep triode region, and in saturation region. So we have to define the noise or the spectral density in all the regions, and we have certain VGS and VDS. So basically in triode region, we have VGS and our VDS equals to 0. And this means it's operating symmetrically, and we have a uniform inversion in triode region. And when VDS equals to 0, then the MOSFET is simply acting as a resistor, and the mechanism of current in the MOSFET is similar as of a resistor, and it is due to the drift of carriers. Although the charge carriers are formed due to the inversion in MOSFET, but the operation is very similar to a resistor. So it turns out that the noise is also exactly same as of resistor. So in deep triode region, the MOSFET is nothing but a conductance of GMOS, and it is represented as a conductance GMOS given by mu Cox omega width by L times VGS minus VT. Now, if we have a resistor with conductance GMOS, then noise spectral density would be nothing but 4 kT GMOS, and thus we have spectral density, this 4 kT GMOS. And in saturation region, there is a contribution of 2/3 of Cx, as here as CGD. Basically CGS, due to the pinch off, has a contribution of 2/3 Cox width by length, and thus the 2/3 factor multiplies to 4 kT GM, and we have 8/3 kT GM at operating point. Just like all small signal parameters of MOSFET, which depends on operating point, the noise also depends on the operating point. And in general, to define the noise in MOSFET in all regions, we have a general equation for spectral density for noise, which is mu 4 kT by length square times the charge and its magnitude. So the noise in MOSFET is also also due to thermal fluctuations in the carriers, similar to resistor, and thus by this quantity we have a white noise curve when plotted spectral density against the frequencies. So now we have a circuit with a number of MOSFETs, and we have certain Vout, and we find the transfer function from every noise current source to the output, and we will have the output to be a superposition of all these noises and current sources, or basically superposition of all these noise current sources. And because these noises from different devices are uncorrelated, so we can exactly write the equation just like a resistor, and we have seen this in the case of resistor as well. And in addition to a thermal noise, there is also a flicker noise in the MOSFET, and this happens to have a different spectral density. So we have our MOSFET, we have our inversion layer. So the charge in the inversion is what is available for conduction, as we know, and the charge in the inversion layer equals to the charge on the gate. So assuming that there are no fixed changes in the dielectric. Now what happens, it turns out that the interface of dielectric and the semiconductor, there are trapped charges, and like thus the trapped charges are randomly trapped and released with different time constants. So this gives us a flicker noise resulting in some randomness in the current. So now we have two current sources due to thermal and due to flicker noise, and those both like literally adds up, and again we can um, realize this like this in practice. We represent that sum. So the spectral density of flicker is basically somewhat different from the normal one. It is kid by L square times inverse of the frequency, and it is inversely proportional to the frequency. So if we plot both spectral densities due to the current sources due to noises in log scale over a frequency which is also in log scale, so this curve is due to the inverse proportionality to the frequency, and it is of a flicker noise, and this curve is her white noise due to thermal randomness. And that's what the point of intersection of these two, or the point where these two are equal, is called f 1 by f, and it is known as flicker noise corner frequency. And dependent on that, our curve of noise in MOSFET looks like this over a frequency. And now the thermal noise is more fundamental phenomena than the flicker noise, as it is just related to the absolute temperature and the fact that we have some current flowing. Now flicker noise is related to the trapped, and thus how clean the fabrication is. And if we take two MOSFETs from different vendors and bias them at same GM, so both will have same thermal noise, but the different flicker noise and very different flicker noise. So this is the case. And now, as we said, the autocorrelation function is the inverse Fourier transform of the spectral density, and the mean square value of variance is basically integral of spectral density from 0 to infinity. Now we integrate our spectral density for flicker noise, we will get infinity for very low frequency. And here lies the fundamental problem with the theory itself. It is not clear that what happens to the flicker noise at very small frequencies. Thus we have to impose some lower limit to the integration when it comes to flicker noise. And in case of PMOS, everything is similar to similar to the case of NMOS. There are many criteria for choosing NMOS and choosing between NMOS and PMOS. One primary thing is the mobility, but generally the mobility of NMOS is higher, and they tend to be used in higher speed application. But flicker noise also plays important role in choosing between PMOS and NMOS. And now we will look at the noise calculation in common source amplifier. So let's take a circuit of common source amplifier where we apply the input at gate and we take the output at drain. So from the basic analog course, we know our common source amplifier circuit, and at this point we know this is what we get, and our GM is basically given by mu Cox width by length times VGS minus VT. Now we will assume capacitor C at the output in order to calculate the mean square value of the variance, and we should have for the sake of calculating the mean square value of the variance, we should have the finite bandwidth, and that bandwidth will be provided due to this C. To calculate the noise, we set the large signal to 0, and as we set the large signal to 0, there is no VGS, and thus in small signal picture, this turns out to be an open circuit. Then we have C, then we have current source due to the noise in MOSFET, and we also have resistor which is to the small signal ground, and this resistor is represented like this, and it also has its own current source due to the noise. And all we have basically over here is a pair of two parallel current sources due to noises, and which adds up and passes through the combination of parallel RC. So now we have to find out the transfer function from the current source, or the IN of R to the output, and IN of MOS to the output. So basically V naught is this is the impedance due to the parallel combination of RC, and this is the sum of currents. So basically this is our transfer function, and now we have to express this in terms of f, and that will give us the spectral density and spectral density of the output, and we can integrate that to get the mean squared value of the variance. So basically from this equation we have the spectral densities, its addition, and we have everything in r squared, as we know that we have a magnitude and its squared times the spectral density. So now what happens is from this we have 4 kT by R due to resistor. We have 8 by 3 kT GM due to the MOSFET, which is MOSFET noise. And we also consider some flicker noise times this factor. And what we do is for these three factors, we plot a curve like this. And we also have in multiplication this factor, which is basically at very low frequencies, it is R square, and then it goes to 0 for higher frequency. And these two curves, we should be multiplying, and the final curve will basically look something like this, and then depending upon the bandwidth it will somewhat go down like this. So the curve will somewhat look like this. So now we will calculate the integrated noise or variance. So basically variance is also called as integrated noise. And for simplicity, we will ignore the flicker noise. So let's ignore this term of flicker noise for simplicity. So we have this equation. And now when we take 8 by 3 kTgm common from this, we are remaining with 1 plus and some values in this. So we have contribution from two parts, and this contribution comes from MOSFET and this contribution comes from resistor. So what is the relative contribution of MOSFET and resistor? So given the common source amplifier has very large GM value, and we cannot comment that most of the noise, like we can comment that most of the noise is contributed by the MOSFET and not by R. As GM is very high value, the whole contribution becomes very less. So very less than 1 in case. So now the root mean square variance is given by integration 0 to infinity of our spectral density, and basically integration of 0 to infinity gives us somewhat this kind of value. And after cancelling few terms, we can do a sanity check by assuming that let's say the MOSFET is not there. So all the terms due to MOSFET, when we cancel them out, so the above equation breaks down to KT by C, and that's how we do the sanity check. So we model the noise in the MOSFET as our small signal model looked like this. So this is how we modeled the noise in the MOSFET, and our small signal model looked like this. Thus the total current from drain to source is nothing but GM plus IN, and here we are ignoring the value of VBS and VDS for simplicity. So we can also parallel or alternatively think of it as not a change in current but a change in gate voltage, VGS. So this is how we can realize that at gate voltage we have some change Vn in the gate voltage, and that's why we are getting a change in current. But let's not look at the change in current, but let's take it alternatively as the change in gate voltage. So this will give us the current Gm times VGS plus Vn, and if both things are pointing at the same concept, so from that we have In equals to Gm times Vn, and that's why our spectral density due to voltage source is Sin divided by Gm square, as spectral densities are related to the squared voltages and squared currents. So that's why our SVN is nothing but 8 by 3 kT by Gm. So now MOSFET has 3 terminals. So the current noise is the current source that appears between drain and source, and voltage noise is something that appears in series with the gate voltage. So we apply on the input to the gate over here, and most of the times we are interested in comparing the noise to the amount of the large signal that we have at input, and in this case VGS is the large signal. So basically let's say we modeled our noise using a current. source like this. And now in order to compare the noise to the input signal, which is basically a large signal, we have to calculate the current, like we have to calculate the current due to the VGS, and then compare that current to our IN, and which happens to be GM VGS, the current, and we have to compare it with IN. But there is even a simpler way if noise is represented by the voltage source. So as we discussed earlier, since Vn simply gets added to VGS, so by comparing the magnitude or some metric value of Vn, um, or some metric of size of VGS, we could easily like compare them, and the magnitude or some metric Vn size of VGS, which could be amplitude of root means, like which could be amplitude of VGS or root mean square value of VGS, we can compare the large signal and the noise, and we can take the like signal to noise ratio, and we can comment on that. So let's take a case where we will not consider the capacitor at the output, and so the noise will not be band limited, so we cannot calculate the variance, but we will be satisfied only by calculating the spectral density. And let's see how. So we want spectral density of the output voltage end. So again, what we will consider that large signal is 0, and if we consider the large signal 0, then in small signal model, this one gets open circuit. We have the current source due to the noise IN. We have the resistor connected to the small signal ground, and the resistor comes with its own current source due to the noise. So from this, the like it will like now from this we can say that we have two parallel current sources which will just add up, and it will flow only through R as there is no C. So now based on that, and we know that spectral densities are related to the squared values of voltages and current, we are getting this equation, and by putting the values of spectral densities for the resistor and for the MOSFET, we are arriving at this equation. So now let's take an amplifier. So basically this is our case, and we are discussing when there is no capacitor. So let's for an instance move from the topic, and let's take an amplifier with number of devices, and we can calculate the noise from each device to the output, and finally calculate the output noise. So we have resistor, we have MOSFET, we have capacitor and inductor. Even though capacitor and inductor don't dissipate or don't provide any noise to the circuit, but they do influence the noise of the circuit. So like let's say we have 0 input, and we can calculate the output noise. We can take a noiseless version of the same circuit where all the components are noiseless, and apply some noise input Vn in, and Vn in is such that the output of the noiseless circuit is Vn out. And over here we said that we are providing no input, and due to the noise we are getting Vn out as our noise output. Now what we will do is we'll take all the components noiseless, but in order to get a Vn out, we will apply some Vn in such that we are getting Vn out. And this Vn in is not something that is present already. It is something that is used for calculation, like calculational convenience, and known as input referred noise. And the way to calculate Vn in is first we calculate the transfer function from noise of each of the component to the output, and that will give us the Vn out, and we divide the Vn out by the transfer function or the gain between input and the output point. So basically the reason that this is convenient is that let's say we apply input voltage as current, or let's say we apply input voltage as signal, and we can immediately compare that large signal with the input referred noise, and see whether the signal to noise ratio is sufficient or not. So let's do this calculation for our case over here. So what is happening over here? So now we have points from A to B, and we have a transfer function from A to B, which is nothing but minus gm r, as this is a common source amplifier. And we said that there is no C over here, but we know that at the output we are getting this equation, and this equation is from here. So we know that the transfer function from point A to B, or from Vi to V out, is basically the gain, and which is minus gmr, and thus V naught equals to minus gmr times Vi. So Vn out is nothing but minus gmr times Vn n, and the spectral density of Vn n is basically spectral density of V out divided by the gain squared. So basically it comes out to be this value. This means that we have a noiseless circuit, and we have a in series voltage source, and it has the spectral density of this value. So it has a spectral density of this value, and it turns out that the first term, if we observe, there is a first term which is nothing but the input referred noise of the MOSFET itself, and we derived it from here, like it's the input referred noise for the MOSFET only. And so if we would have used the alternative model for MOSFET, let's see this one. So it would have had been immediately clear that the input referred noise would be this value plus something, and that something, it sometimes is convenient and beneficial to model the noise of the MOSFET as input referred noise, or the input referred noise to the referred large signal instead of the output parallel current. And basically we have these two terms. So the second something term, we said like it is something, so that something is nothing but if we look at the term, it can be written as 4 kT by R divided by Gm square, and 4 kT by R is nothing but the spectral density due to the current which is due to the resistor. And the transfer function from point A to point B, or the like transfer function from the input to the drain current, is Gm, and thus that Gm squared, as we know that spectral density always talks about the square values, so that spectral density divided by the gain square is nothing but the spectral density divided by the transfer function from A to B squared will be our second factor, and that's what our second factor is. So that's how we can intuitively derive the noise. So in general, we have number of amplifiers. The noise added at output of something will get divided by the square of the gain referred to the input. So basically, by just looking at this circuit intuitively, we can say that SVN is basically S spectral density from the MOSFET plus something value, which is basically spectral density due to the resistor, divided by the square of the transfer function from point A to B, or basically gain from A to B squared. And that's how we derive intuitively. So I think that's all for this video. Thank you so much.